Hello, in continuation to my earlier video where I discussed the importance of organometallic compound, I would like to add something to have your interest towards the organometallic chemistry. As I said that this Ziegler-Natta, your catalyst, which was crowned by the award of Nobel Prize in the year 1963, Ziegler and Natta in the year 1963. Prior to this, in the year 1912, Victor Grignard got Nobel Prize for his discovery as Grignard reagent. And the newness and the importance of the organometallic chemistry you can evidence from the continuous conferring of Nobel Prizes in the year 1973, then 2005 and 2010. So you can have the idea how new it is and what is its importance. Now going to the classification of organometallic compound. First, I will discuss the organometallic compounds of main group elements. The main group elements are any of the chemical elements belonging to S and P block. So this is the S and P block of elements of the periodic table. They are the called as main group element. And the S block is having group 1 and 2. Nowadays it is written group 1 and 2, and this P block is from group 13 to 18. So the main group metals of the P block, excluding elements like nitrogen, phosphorus, oxygen, sulfur and halogens, which are more electronegative than carbon, form essentially volatile covalent organocompounds in which the ionic character tends to increase as expected on going down any group of the periodic table. If you go down in the group of the P block element, you will find the metal downward. So there will be difference of electronegativity in comparison to the carbon, and you can assess the nature of the compounds which you are having the periodic properties knowledge. Thus, the compounds of the lighter halogen and the chalcogens are excluded from the field of organometallic chemistry, but not the organic derivatives of boron, silicon, arsenic, because they are considered as metalloids. The organometallic compounds of main group elements generally forms sigma covalent bonds. So, but this S block are having the exceptions. They are largely not all, they are largely forms ionic your compounds. So this P block forms mainly the sigma covalent bonds with the carbon, whereas the S block forms ionic your covalent ionic compounds and some of the exception like lithium, etc., which I will discuss later on. The polarity of the bonds depend not only the difference in the electronegativity between the metal atom and the carbon, but also on the metal orbital which are available, then the steric requirements and the polarizability of the electrode cloud. It has been found that the order of polarity in the case of alkali metals, lithium to carbon is less polar compared to the sodium to carbon than potassium to carbon and then to rubidium to carbon and then to cesium to carbon. And thus the alkyl of the sodium onwards are more ionic and less covalent than those of lithium. Even it has been found that lithium forms compound with the bridging alkyl group like beryllium, magnesium and aluminum, and appears in the category of what? Electron deficient compound. I would like to mention here one example of lithium which is having your structure. The formula is LiCS3 whole 4. That means Li4CS3 whole 4. And it is when we go for the this structure, so go for the structure like it is having a cube in which alternate corners are occupied by lithium, this is also lithium, Then the alternate will be this one also, lithium. And the rest 4 alternate corners are occupied by CS3, then CS3, then CS3, then CS3. So, if you look at the lithium, then lithium is bonded to, linked to the methyl group, and the number of methyl groups are 3. 1, 2, and then 3. If you look to this lithium, this is also having same feature. Any of the lithium, if you find, then this lithium is linked with the 3 methyl group. The conventional method to explain the bonding, it is not possible, and this lithium shows that it is having the less polarity and towards the covalency, and it falls in the group of electron deficient compound like beryllium, CS3, whole 2, whole N, then your different oligomers of dialkyl magnesium, and then you are having the aluminum dimers, L2, CS3, whole 6. So this alkali metals, lithium, falls in the also group of electron deficient compound. The other example of this category of your main group elements are the sodium also having a compound which is ionic type C5H5. Then potassium is also having your C6H5, that is the phenyl one. This is cyclopentadienyl, I had already discussed in earlier videos. Then the naphthyl sodium, this is Na+, then C10H8. So these are your stable ionic organometallic compound, and the stability depends on the organic radical, because the stabilization of this negative charge through the pi electron density of C5H5, C6H5 and C10H8 rings. So this is stabilized by this negative charge is stabilized through the pi electron density of these rings. So I am stopping here. Let us have some other examples like of your main group, like RMGX, then beryllium I discussed in the polymeric form, but it is also having the dialkyl. Then boron is also having CH3 whole 3, arsenic, and that I had already discussed. Then the silicon is also having your organometallic compound. Tetraethyl lead I discussed earlier, and the tin compound. So this is all about the organometallic compound of main group elements, just idea about that. Thank you very much.